All right. Now, here's an interesting example. Given the graph of the function, I want to graph what the derivative is, but I don't even know what this equation is. Yeah, I could go to this calculator and I made an equation that kind of matches this. But what I want to do instead is I want to use this idea of the slope of the tangent line in order to determine what the graph of this function would be. And there's certain points that you can check out to see where your function should exist. I'm going to make this just slightly bigger, actually. All right. So if we imagine our tangent line as it's coming up right here, it's going to be some positive value. And then at this point up top, it flattens out. So it kind of comes up and it's a positive line. And then when it reaches the top, at some point or another, it turns flat. And when it turns flat up top, its value is 0 because our slope of our tangent line is 0 at that point. So I could say that right here, if I'm graphing f prime of x, so f prime, just f prime, the derivative, it should be 0 at that point. You can do the same thing down here. It's kind of like this negative value, it's coming down, and then it flattens out before it turns back up. So at that bottom, that minimum, it's also hitting 0. Okay. Now, imagine this. Whoa, what's going on? Okay, now imagine this. Okay, so at this side of the line, it's going up. And if you imagine these lines that are right there, those lines have a positive slope. So I don't know exactly what the slope of my tangent line is, but I do know that it's positive. So I could kind of make a whoop like that. Then once it hits this top spot, now the slope of my tangent line is heading down. So it's a negative value. So now it is whoop, a negative value, which is nice because it was positive for a little while and then it became negative. Okay, now it's kind of getting negative and it's becoming more and more negative, but then it's got to head back towards 0. It's going to flatten back out. So it gets more and more negative. Oh, it gets more and more negative, but then it changes its mind and starts feeling positive again. But not until it hits this critical point, that's the fancy name for it, down there. After that, it starts being positive again. These are all positive slopes, and positive slopes that are getting steeper and steeper and steeper, so it's going up. So that graph is the graph of f prime, that whole U shape. So we took what was a cubic, we turned it into kind of a quadratic. Ooh, neat. Let's try this a few more times, okay? Because that's kind of goofy to think about. So here are a bunch of functions, and we want to figure out which one is its own derivative, where the slope of its tangent line is the same as the function in and of itself. Really, I just want to do more examples of what we just did. So I graphed them on Desmos, and we're just going to kind of take a look at these things. Now, one thing that's really easy to check is that flatten point. So if we look at sine, it's got a lot of flat points. So right here, the slope of our tangent line is 0. So if we were to graph f of x, it would have a point somewhere down here. And it doesn't have a point there. It's not staying in the same spot. And when we hit here, it also should be 0, and there's no line there. So we want our slope to be the same as what our function is doing. So it seems to be kind of having a 0 and then a 0 here. So the zeros are sort of off. Fun fact, if I change this to f of x, I turn this thing on, here is our derivative for sine. And do you recognize that one? Oh my gosh, that looks like cosine. Ooh, more on that later. Not today though. So, okay, so this one doesn't seem to be its own function. Be its own derivative. So that one doesn't work. So sorry. Let's try this one. Okay. So now this one looks good, okay? Because we're at 0. What's our slope? It's 1. And then here our slope is 1. And here our slope is 1. And here our slope is 1. So it seems to just be 1 all the time. So it seems to be just this horizontal flat line all the time because it doesn't seem to be changing. Let's check. So if I change this to f of x, all right, yep, it's just a boring horizontal line all the time. So I've set this up so it just does the derivative for me. Your graphing calculator can do this too, by the way. So boop, boring, bleh. Nah, it doesn't match up. Sorry. Let's try this one. So at first, we've got a really big number for our derivative, and then it kind of gets smaller and smaller and smaller. So our derivative is getting smaller and smaller, but our graph is getting bigger and bigger. So it doesn't seem to be matching up. Let's double check though, and see what happens if we look at f prime of x. Ooh, look, it kind of makes this goofy shape. Well, that's goofy and weird. I wonder what that could be. Something else. It almost looks like a 1 over x function, like the reciprocal. That's what it almost looks like, but it seems to be messed up a little bit. So it seems to be something like that. But I don't really know. I do know, but I'm not telling you right now. But it doesn't match up. Okay. So sorry, you don't work either. Okay, let's check this one. So we were just doing this with a cubic. So we're coming down, so we have a negative value, but these are positive values. Here we've got a slope of 0 and it's meeting at 0, so that's good. And then it's kind of coming back up and now it's positive. So it should have something down here. It should go through here and then come up somewhere over there. Let's double check, see if it does that. F of x. Oh, look, cool, it did that. So that we got something down there. It goes through 0, 0, and it comes straight up. Cool, that quadratic turned into a straight line. How interesting. What's your slope, straight line? Oh, your slope is 2? Oh, that seems interesting and somewhat related to this, but it's still not the thing that we're looking for. Oh, sorry, you don't match up either. All right, last one, E. Oh, okay. So we've got like a slope of like basically 0. Ooh, and the function seems to be about at 0. And then we're kind of coming along. And as we move along here, our slope is getting bigger because right now it's flat. And as we move along, it's getting steeper and steeper and steeper. And e to the x seems to be getting steeper and steeper and steeper. So it might be this one. And it is because I saved this one for last. You can do process of elimination and then, oh, boom. So you can't see it unless I make them flash. But look, they match up. E to the x seems to be its own derivative. When you take the derivative of e to the x, it's still e to the x. Oh, that's really cool. It's one of the reasons why e is actually a very cool, exciting number, is because it's its own derivative. E is representational of growth. And so when you take the derivative of it, it's still growth. So the growth of growth is growth. So the answer for this one turns out to be this e to the x. The other ones don't quite work, but I have kind of given you a little bit of a preview of what we're doing next, which is this, the power rule. And I believe you have seen this in your physics class if you're taking physics right now. It's a shortcut and it makes derivatives so much easier. Coffee drink so you can pause and write all that down. There's different ways to notate this same thing. So if we got f of x is x to the n, all you need to do to find f prime of x, the derivative, is you drop the exponent in front and you lower the degree of the exponent by 1. And so this is the same as this. So there's 2 ways of writing derivative. You can write f prime of x, or you can do d over dx. So the derivative so the slope as x is changing. So this is just another notation for the derivative, if you ever see that. So the derivative with respect to x is what it means. So let's try it out. Oh my gosh, it's so much easier. So we've got 12. So that's a line that's just sitting perfectly straight. So we've got x to the 0 next to that. So when you do y prime, why am I doing y negative? Y prime, you get 0 times 12. x to the negative 1, but all that stuff multiplied together is just 0. So the y prime is just 0. Cool, which is good because we should always have our constant lines should have a constant slope of 0. If we have y equals x to the 7 and we're interested in finding that thing's derivative, all you need to do, y prime, is bring that 7 into the front, 7, and then drop that degree by 1. So the 7 becomes a 6. Ta-da! It gets a little goofy if you've got fractions, though. So what I like to do is I like to rewrite this first. So y is really x to the negative 5. So I can write it a little bit more simply. Then it's a lot more clear. So y prime equals negative 5 x to the negative 6. You could write that back in a more nice form because we don't like to leave negative exponents. We get negative 5 over x to the 6th. Finally, if we've got a radical, this is y equals x to the 1/5. Radicals are fractional exponents. So then y prime is going to be drop that exponent in front, 1/5, x, and we have to do 1/5 minus 1. So that's negative 4/5. 1/5 minus 1 is negative 4/5. So if we wanted to write that without a negative exponent, y prime equals 1 over 5 fifth root of x to the 4. Boom. Okay, so just a couple more examples of doing that rewrite, differentiate, and simplify process. So your first job is to rewrite this thing. So you got 2/7 x to the negative 4. We don't want to deal with it inside of that denominator. Now we want to differentiate that. So we keep our 2/7. Our negative 4 comes in front. And then the exponent on that x drops one more spot. So it goes from negative 4 to negative 5. Now we want to simplify that. So that is 4 times 2, that's negative 8 over 7. And we don't want to write our answer with negative exponents, so x to the 5. Now this one, we've got 2 x's. Ugh. If you've got 2 x's, can we combine those two things? So, well, let's see. Let's rewrite it. And we're going to do 2 rewrite steps this time. We're going to make it an x to the 1/2 over x. In our second rewrite step, I'm going to use the quotient rule for exponents. I can do 1/2 minus that x to the 1 in the denominator. So this is really x to the negative 1/2. Now I'm ready to differentiate, now that I just have one x. So that is going to be y prime. Why don't I have y primes up top? Just notice that. Y prime, this is y, and then this is y prime. Sorry, that was going to bug me, and I'm sure it was bugging you. Okay, so y prime equals, we're going to bring that negative 1/2 in front. X and that negative 1/2 exponent needs to be subtracted by 1. So it becomes negative 3/2. Now to write it nicely, you say that y prime equals 1 over 2 square root of x cubed. Finally, what if you have things being added and subtracted? Well, guess what? You can do those in separate pieces. So take care of the derivative of each piece. So derivative of that thing, and then derivative of that thing. So first thing I'm going to do is I'm going to rewrite g of t a little bit more better. So I'm going to make this a t squared minus 4t to the negative third. When I look to find g prime of t, I can just do the derivative of those individual terms when they're being added or subtracted together. So we get 2t, and then we do -3 times -4 when that negative exponent drops in front. So we get positive 12 t to the -4. I'm kind of in the way. -4. Okay. All right, well then g prime of t, if we want to write this nicely, equals 2t plus 2t, 12 over t to the 4. Final problem, I think, is this one. So we've got too many x's. This has got the same problem that we had before. What I'm going to do is I'm going to simplify f of x by dividing those two things in the numerator by x. There's another way to do these that we're going to learn about next time, but for today, let's just do this because that other rule is weird. So I'm going to divide 4x cubed divided by x gets us x squared, and then 3x squared divided by x is 3x. All right, now we're all set to find our derivative. F prime of x equals 4 times 2, the exponent of 2, 8x, plus 3 times 1, that's still 3, x to the 0. But if we've got an x to the 0, well, that seems silly. X to the 0 is just 1. So we get 8x plus 3 times 1, so it's just a 3. 8x plus 3, that's f prime. Boop, boop. All right, now I hope that's it. Nope, I'm wrong. This might end up in a bonus video. Again, I got too many x's. There's a way to do this as just as is, but they got too many x's. So I want to kind of simplify this thing down a little bit. So I get y equals x cubed. So I'm just going to distribute. Plus x. Y prime is going to be 3 x squared plus 1 x to the 0. But again, just like the last one, x to the 0 is just 1. So we've got 3x squared for y prime plus 1. Got some radicals in this next one. Same process. F of x equals x to the 1/2. Mel's had enough of this video. Minus 6 x to the 1/3. Let's see if I can do this with a cat right here. She's going to bite me here pretty soon. So when I try to find f prime, I need to bring those exponents in front and drop them by 1, which is going to get a little weird. So I get 1/2 x. 1/2 minus 1 is going to give me -1/2. Minus, I'm going to write it out, 6 times 1/3 x. 1/3 minus 1 is going to give me -2/3. So f prime of x equals, so that 1/2 x and that x to the -1/2 has got to go into a denominator. So we're going to call that 2 square roots of x in the denominator minus our 6 times 1/3. 1/3 of 6 is 2. Keep that up top. And that x to the -2/3 needs to go in the denominator. So we got the cubed root of x squared. Can we be done? Yeah, that's it. So there's two alternative forms of derivative. One of them is cooler than the other one. This is the cool one. So our power rule lets us evaluate derivatives very, very quickly. The alternative form of a derivative helps us ensure that we have a derivative at particular points. Our cool new power rule doesn't allow us to do like absolute value derivatives because we don't know how to do absolute value. There is no exponent for absolute value. We can do things like square roots, but we wouldn't be able to do absolute value inside of square root inside of absolute value. That's just not going to work out well for us. So alternative form helps us find things. The power rule is something I think you've known about for a little while, but now I'm telling you officially, it's good to go. Use it. It's great. That's it for today's video. Thanks for watching. Have a good day.